In Britain today, there are almost 40 million domestic appliances which have one essential characteristic in common: the use of natural gas, which is essentially methane. We tend to take the many benefits which result from the correct use of natural gas for granted. Scientific understanding of this energy source has been with us for a long time. However, the technical application of natural gas has evolved rapidly in recent years. This is reflected in the design changes which are continually being introduced so as to keep pace with our evolving social environment. Amidst all these changes, the natural laws which govern the safe and efficient use of natural gas remain constant. What are the necessary conditions for the correct and proper use of natural gas? Gas pipes run under our roads, delivering the product to each home. The amount of gas used is registered on a meter. Well, let's assume that a supply of gas has been safely and satisfactorily delivered to the point of use. The use of gas involves four basic processes. The gas must be ignited, it must be burnt, heat resulting from combustion must be transferred, and the products of combustion must be disposed of. Well, let's start with ignition. In Britain, natural gas, which comes from offshore fields, is almost pure methane. The gas will only ignite under certain conditions. This will be demonstrated by experiment. Here we can see a simple arrangement which includes an air supply and an energy source with which to trigger combustible mixtures of air and methane. This vertical column indicates the percentage of methane entering the combustion chamber. Methane is gradually introduced into the combustion chamber to the point when the explosion demonstrated that natural gas will only ignite provided that there's a minimum of 5% of methane in the air mixture. Is there a maximum level? Air containing a high level of methane is now entering the chamber. Although the igniter is sparking, the mixture will not light. The methane level inside the chamber is reduced by restricting the supply. Eventually, the relative level of methane present in the chamber falls to the point when... So, by experiment, we've demonstrated that methane, or natural gas, the kind used in British households, will only ignite within a narrow band of mixtures with air. Only when there's between 5 and 15% by volume of methane present in air can ignition occur. A source of energy is also required to ignite the mixture. Here the spark, a low amount of energy, is being misdirected. This energy must be released in the correct zone if ignition is to occur. Using a match, the ignition zone is easily located, and so the appliance is lit. However, the amount of energy released within the match flame itself is far in excess of the energy required to obtain ignition. In the case of a low-energy ignition facility, like a spark, the ignition zone is critical. The spark must be accurately placed. When natural gas ignites, combustion takes place and energy is released. In order to understand the combustion process, we must first look at the respective composition of both natural gas and air. Natural gas, as we've already said, is almost pure methane. It's not always appreciated that methane is lighter than air. Air is made up of 1/5 by volume of oxygen and 4/5 by volume of nitrogen. For complete combustion to occur, 1 more unit of oxygen is necessary. So 4 more units of nitrogen are present. Nitrogen is inert. It plays no part in the combustion process. An energy source in the form of a spark is introduced. This ignites the mixture. Energy is released, and the resulting products are carbon dioxide and water vapor. Each molecule represents 1 unit of volume, so it can be seen that there's twice as much water vapor present compared with carbon dioxide. Of course, the nitrogen, which played no active part in the combustion process, is still present. In fact, it represents almost 3/4 of the products of combustion. Air is an essential ingredient if combustion is to occur. Let's consider a detached house as a box full of air and the lean-to as a box full of methane. For normal combustion, 1 unit by volume of methane requires 10 units by volume of air, the air being made up of 2 units by volume of oxygen and 8 of inert nitrogen. So the actual air inside the house is quickly consumed by burning a relatively small volume of methane. How is this air replaced? By ventilation. Even in a well-constructed house, there's always some natural ventilation around windows and doors, for example. But it's unwise to assume that this will be adequate. In the case of a cooker in a kitchen, the appliance is designed to function in an environment where there would be continual acceptable levels of ventilation. Because ventilation is necessary in order to get rid of steam and unwanted odors from cooking. A central heating boiler of 100,000 British thermal units per hour heat input requires 1,000 cubic feet of air every hour for combustion. In an average-sized kitchen, this volume of air represents twice the volume of the room. Purpose-made ventilation must be provided to supply this central heating boiler, which devours 80 pounds of air per hour. Without this opening, air would flow through this 1/8 inch gap under the kitchen door at 8 miles an hour. We can demonstrate by experiment that an adequate air supply is essential for proper combustion. In this combustion chamber, the supply of air is cut off. The flame gradually consumes all the available oxygen in the chamber and so cannot continue to burn. Air bricks or similar ventilators are a necessary part of any domestic situation. Modern cooker burners, indeed most burners in use in gas appliances today, are the aerated type. Pressure forces natural gas into the burner throat and air is entrained. This is called primary aeration. The mixture leaving the flame ports ignites, provided it's within the flammability limits. secondary air necessary for the combustion process is drawn from air surrounding the flame. Hence, burner design is an important feature. The flame ports should be deep enough and small enough to ensure that the flame remains stable. A stable flame is usually a sign that the burner is functioning efficiently. This is true of cookers, fires, boilers, or indeed any other domestic appliance using natural gas. Energy is only useful if it can be harnessed in such a way that it will benefit the end user. In the case of gas, the initial method of transferring heat energy is almost always by convection from the hot products of combustion. Convection currents transfer the heat from the flames to the food. Heat travels through the solid food by conduction, and so the food is cooked. The cooker grill combines convection and radiation. Hot gases transfer their heat by convection to the grill, which then radiates heat energy down onto the food which is to be cooked. Convection currents, in the form of hot products of combustion, are the initial way in which heat is transferred. In the case of a water heater, heat energy passes into the water through the heat exchanger. Heat flows through the heat exchanger by conduction. The water inside is then heated by conduction from the inner wall of the exchanger and by convection in the water itself. A gas central heating boiler works in much the same way. Hot convection currents pass over the heat exchanger, heating the water inside by conduction. Waste products pass out through a flue into the outside atmosphere. The products of combustion, as we've seen, are carbon dioxide, water vapor, and inert nitrogen. These products are in themselves harmless, so why must we get rid of them? Well, let's close the flue and see what happens. The flame demonstrates the chemical changes which are taking place inside the chamber. It's using up some of the oxygen inside the chamber and replacing it with carbon dioxide and water vapor. The amount of nitrogen present remains unchanged. Soon the atmosphere inside will be so depleted of oxygen that the carbon, instead of combining with the two parts of oxygen to form carbon dioxide, will unite with only one part of oxygen to produce carbon monoxide, a highly toxic gas. So it's necessary to provide a flue in many circumstances so as to dispose of the products of combustion. The emerging stable flame demonstrates this. Any gas appliance must be regarded as a complete installation, from the entry of air to the combustion chamber to the exit of the products of combustion into the atmosphere. In flues, only very small forces are available for inducing the necessary upward movement of gases. These forces arise from the gases inside the combustion chamber expanding when they're heated. Therefore, these gases have less weight per unit volume than the outside air. In other words, they're less dense. So the hotter the gases inside, and the greater the vertical length of the flue pipe, the more effective the flue. It's important to understand that greater vertical height, and not simply length of flue pipe, which might run diagonally across the wall, will provide more effective fluing. The horizontal position is virtually ineffective. Terminal design and positioning are also important, for it's these which help to promote updraft and prevent downdraft. Downdraft can have adverse effects on burner performance, so draft diverters are provided in many appliances. These divert downward currents of air away from the burner flames. Terminals should be located, where possible, in freely exposed places, where wind forces can help rather than hinder extractive effects. This wind tunnel model is being used to gather terminal design data, which will eventually influence practical applications. In the case of balanced flue appliances, pressures at the inlet and outlet are in balance. The combustion chamber and flue are completely sealed off from the room. Hot gases from combustion pass through the heat exchanger and flow out through the inner exit ducts. Air required for combustion enters the combustion chamber through the outer air entry ducts leading from the terminal. The development of the balanced flue represents an important step towards perfect fluing. Today's advances in design, more effective installation, and better maintenance practices have grown out of a wider understanding of the fundamentals of gas utilization. These fundamentals are: the gas must be ignited. Combustion must take place in order to release energy. That energy is transferred by convection, conduction, and radiation. And the waste products of combustion must be disposed of. New developments will undoubtedly appear in the future. However, the four main fundamentals of gas utilization remain as the true basis upon which new ideas must be built.